Hello, fifth year, and welcome back. Today we're going to be moving on to our next booklet of the higher course, which is called Refraction of Light. You will be able to get a blank copy of this on the Firefly blog page, and obviously you can tune in to OneNote. I've added it to the content library over on the left for you to view at any time. You will also find a copy of the question booklet and a copy of some numerical answers so that you can check your working as you go. Remember, any questions that you complete, you should open up your personal tab. You go to your January lockdown work and you can add these questions here, which allows me to view them and write on some feedback for you. So today, refraction of light, and this topic has a little bit of the course from National 5 to begin with. Refraction leads on from our reflection topic, which we looked at. So our learning outcomes you can find here at the start of the booklet, some new formulas that we're going to use, and what are the things you need to know to make sure that you are ready to answer any exam questions on this topic. First of all, we go to start with just a little bit of revision about light, which hopefully most of us are familiar with. That is part of the electromagnetic spectrum. And we can see it with our visible light, the rainbow colors and the visible light spectrum, as we would call it in physics. Part of the electromagnetic spectrum where we have all of our different wavelengths and frequencies, all of which travel at 3 times 10 to the 8 meters per second, or 186,000 miles per second in air. But the unit that we should be familiar with is the meters per second. The distance from the Earth to the Sun is 93 million miles, and this takes light about 8 minutes to travel. So just a little bit of revision to remind ourselves about the sort of scale that we're talking about here when we talk about the speed of light. Reflection, something that we all probably use every day without knowing whenever you look in a mirror. And this is from the National 5 course, where we have our incident ray, which is going to hit this flat plane mirror, and then it's going to bounce off the mirror and move away back out into the room. What we would see if we were in class and able to carry out this experiment is that our angles of incidence and our angles of reflection are of course equal to each other. This line that I'm drawing in at the moment, the broken line with the green pen, being the normal line, the line which is drawn at 90 degrees to the surface of the mirror. So we would have our angle of incidence taken between the incident ray and the normal, and we would have our angle of reflection taken between the reflected ray and the normal. And we can add in both angles are equal. So our little conclusion here, add a normal to the diagram. We've done that, measure the angle of incidence and label this in the diagram. We can see that they're both equal. Draw the reflected ray. We've been able to do that. And state the law of reflection. And our law of reflection is that the angle of incidence is equal to our angle of reflection. And if you remember that fact, that will keep you right if you see any of these questions in the multiple choice about reflection and refraction. So just a little bit of revision there, that topic. In terms of questions, and at the start, there isn't really any questions on reflection as it is just National 5. So we'll move on to the new content, which is of the higher material. So refraction. Refraction is when light and other forms of electromagnetic radiation travel through the air and encounter a boundary. Light travels at its greatest speed in a vacuum when it's traveling through space towards Earth. It also travels at nearly this speed in gases such as air. Light travels through different materials such as perspex, glass, water, or diamond. These are more dense than a gas or a vacuum. Air is marginally more dense than space when we consider its optical properties. However, if you compare air to diamond, due to the structure, you can imagine that the diamond is a lot more dense, and when the light encounters that boundary, something happens to that light that it doesn't just pass straight through as you would expect. The light changes its speed when it reaches these mediums. If you were to imagine yourself running along the school track, and at the end of the track we were to put a 20-meter sand pit, you would encounter the sand and your speed would decrease. You're running through the air on the concrete, you encounter the sand, your feet are then having to push through this material. Imagine the light traveling through the air, entering the glass or the diamond. It's having to then work its way through this more dense material, changing its speed. Something else which happens when the speed changes as it enters into a medium is the direction of the ray is caused to change. This experiment here investigates the relationship between our angle of incidence as the light enters our rectangular prism and what happens to the light inside this rectangular prism. We will have our angle of refraction. The light, as it crosses inside the block, is going to change direction. It's going to bend towards the normal. And then as it leaves the block, it's going to bend away from the normal. So let's draw in our normal line here. And we take our red pen and our ruler. Now, generally the light enters the block parallel to the angle that it leaves the block. What I'm going to do, actually, I've used the wrong color of pen, so we're going to rub out this green line. We wanted to use a red line for this one, because this is our light as it leaves the block. And use our green pen to draw the normal. So the normal is this one here, which we're looking for. Just used the wrong colors. So we now have our incident ray, our refracted ray, and our ray as it leaves the block. So a ray of light from the box is shown into rectangular perspex. Mark the angles of incidence and the angle of refraction are measured in each case. So what we would have here is our refracted angle, which is going to be theta 2, and our incident angle, which is going to be theta 1. We would carry this experiment out in class, and what I'm going to do just now is pause this video and we will direct you to a separate video where you can see this experiment being carried out. Thank you.